Businesses know that customers often respond to background music. Do they also respond to odors? A study was done in a small pizza restaurant on Saturday evenings in May. One evening, a relaxing lavender odor was spread through the restaurant. On another evening, a stimulating lemon odor. A third evening served as a control with no odor. The 3 evenings were compared in many ways: weather, customer count, and so on. So we are willing to regard the data as independent random samples from Saturday evenings at the restaurant. The table below contains data on how long, in minutes, customers stayed in the restaurant on each of the 3 evenings. Do a complete analysis to see whether the groups differ in the average amount of time spent in the restaurant. Use alpha equal to 0.05. Let mu1 be the population average amount of time people would spend in the restaurant, given that the odor was lavender. Mu2 would be the population average time that people would spend in the restaurant, given that the odor was lemon. And mu3 be the average time, the population average time that people would spend in the restaurant, given that there was no odor. We will set up our null hypothesis as follows. We'll assume that these average times are the same, that there is no difference. And we will run an ANOVA test on this to see if we can show otherwise. So not as above. To gather the kind of data we need to run the ANOVA procedure, I used Excel and the descriptive statistics to gather some information about the 3 samples. The first sample has a size of 20. The sample average turned out to be 106.25, and the variance, which is the square of the standard deviation, is 214.9342. I'm going to go ahead and carry these out several decimal places because there's a lot of calculations to do. The second sample, the sample size was 16. The sample average was 91.125, and the sample variance was 265.3167. And then finally sample 3. I'm noticing that these samples are of different size. This one was 18. The sample average 87.8889, and the variance 222.9281. It's important to see if the conditions for ANOVA have been met. One of the conditions is that each of the samples are random or are good representative samples of the population, and we will assume they are. Another condition is that the populations are normally distributed. This condition can be satisfied by simply looking at the distributions of each of the samples and making sure there are no outliers and that they are roughly symmetric. And these are. A very important condition is that the population standard deviations are equal. We can go ahead and assume that this condition is met when the largest sample standard deviation is no more than twice the smallest sample standard deviation. So getting the standard deviations Sample standard deviation for sample 1 was 14.66, which is just the square root of the variance. The sample standard deviation for sample 2 is 16.29, and the sample standard deviation for sample 3 is 14.93. The largest one is 16.29, and the smallest is 14.66. So they are close enough. The largest one is no more than twice the smallest one. So we can go ahead and be comfortable using ANOVA to run this test. A couple other things that we're going to need here for our formulas in calculating a test statistic is we need N sub t, which is the total number of data values in our combined samples. So we have 20, 16, and 18. NT is 54. X bar bar is the average of all those 54 data values. So if I take all the values in all the samples, all 3 samples, add them up and divide by 54, the total, I get 95.64815. Now, if the sample sizes were the same, I could have gotten this value just by taking the 3 sample averages, adding them up and dividing by 3 in this case. But they're not the same sample sizes, so that I need to bring all of the data in and calculate the average. Okay, to get a test statistic, I need to first find what's called SSTR. And I'm going to use the formula. My K value is 3, so I am going to put a 3 in there. And then go ahead and do this calculation. For J equal to 1, I'd have N1, which is 20, times the quantity X sub 1 bar, which was 106.25, subtract my X bar bar, 95.64815, square that, then go to the next one. I have N sub 2, which is 16, times X sub 2 bar, which is 91.125. Again, subtract the overall average, 95.64815. Quantity squared. And then finally, N sub 3, which is 18. X sub 3 bar, which is 87.8889, and then again subtract the 95.64815 and square that. That all turns out to be, do all those calculations and add them together, 3,659.03. So I would get MSTR is going to be the 3,659.03 divided by K minus 1, which is K is 3, and I get 1,829.52. Now I need to go and find SSE, and my formula is, and again K is 3, and for J equal to 1 I have N1, which is 20, subtract 1, and my variance S sub 1 squared, my sample variance is 214.9342, and then go on to J equal to 2. I'd have 16 minus 1 S sub 2 squared, so that'd be the 265.3167. And then lastly, for J equal to 3, I have N3, which would be 18, subtract 1, and S sub 3 squared, 222.9281. And this gives me 11,853.28. And now I have MSE, which is the 11,853.28 divided by NT, which is the 54, minus K3. And I get 232.42. And now I have my test statistic F, which is MSTR over MSE, (1,829.52) divided by 232.42, which is 7.872. Now I'm going to run an F-test, and I will assume that MSTR is less than or equal to MSE. And see if there's enough evidence based on my test statistics, my samples, and my calculated test statistic to show otherwise. And as you have read, if the null hypothesis that the averages are all equal is not true, then MSTR becomes inflated. It gets large. MSE is always a good estimate of the overall population's variance, but MSTR is only good if the averages are equal. And if the averages are equal and MSTR is also considered a good estimate, then these two values are close together, and we won't get a rejection in the F-test. But if the averages are different, and if the sample information is significant enough to show that, MSTR then will be larger, proven larger than MSE. We are using an F distribution here to compare these two estimates of variance. And alpha equal to 0.05. We need a critical value. That critical value, as you remember, depends upon the degrees of freedom from the numerator value and the degrees of freedom from the denominator value. So I'm looking at my test statistic here in MSTR. MSTR's degree of freedom is its denominator. So the numerator degree of freedom is 2. The MSE's degree of freedom, the denominator, is its denominator. So that would be 51. And if I go to the F distribution table then, I will look at the column number for 2, and then looking up 51 for the denominator, that would be the row, and paging through the F distribution table, 51 is between 40 and 60. So being conservative, I'm going to go with the 40, and with a 0.05 level of significance, I get 3.23. And then reject H sub 0 since 7.872 is greater than 3.23. In other words, the 7.872 is far enough away in the distribution from my critical value at a 95% confidence, a 0.05 level of significance, to say that the null hypothesis for the F test should be rejected. Now, saying that the null hypothesis here should be rejected is saying that MSTR is inflated. But MSTR becomes inflated when the averages are different, or at least there is some differences among the averages. So that means that I can reject my original hypothesis and conclude that the averages are not all the same. Another way we could run this test is with a p-value. And to get the p-value, I used Excel to run an ANOVA test on my data. And later on the page, I have a PDF file that you can look at with instructions on how to do that. The Excel procedure gives you a what's called an ANOVA table, which you'll want to understand how that's constructed. Again, read some of the other material on this page to do that. The p-value from Excel turns out to be 0.00104886, which is less than 0.05. And again, of course, these agree, both using a test statistic critical value as we first did and a p-value approach comparing to the level of significance. We reject the null hypothesis. Now, the next step that we need to take is to try to figure out where the differences are. Again, we've shown that there's differences, but we haven't determined where they're at. And we will do that using what's called Fisher's method, and looking at the sample averages and running pairwise tests to see where the significant differences are among the population averages. So later on this page, we will also show you how to do that with a video.